Picture staring up at the night sky, mesmerized by countless stars stretching into infinity. But here's the shocking truth. Everything you see, every shimmering light, every swirling galaxy, makes up less than 5% of what's actually out there. The other 95%, it's missing, vanished, a cosmic mystery so baffling that even the brightest minds in physics still wrestle with it today. Where did the universe's energy go? Why can't we detect it? And what invisible forces are secretly shaping the fate of everything around us? This isn't science fiction, it's the reality of our universe. Scientists call this missing chunk dark energy and dark matter, two shadowy concepts that defy everything we thought we knew. Dark energy rips space apart, pushing galaxies away from each other faster than light. Dark matter clings to the edges of galaxies like an unseen glue, holding them together against the chaos. Together, they dominate the cosmos, yet we can't touch them, see them, or even prove exactly what they are. It's like living in a house where 95% of the rooms are locked, and you can only guess what's inside by listening at the doors. But here's where it gets thrilling. Over the years, researchers have spun 30 incredible theories, some wild, some brilliant, all mind-bending, to explain this astronomical missing piece. Maybe dark matter is made of primordial black holes from the birth of the universe. Maybe dark energy is the fingerprint of hidden dimensions curling in on themselves. Or perhaps we're witnessing the slow unraveling of reality itself. In this video, we're diving deep into these ideas, from the eerily plausible to the edge of imagination. Buckle up, we're about to journey into the greatest unsolved puzzle in physics, where every answer leads to 10 new questions, and the universe keeps its greatest secrets just out of reach. First up, what if dark energy isn't some exotic force, but something far stranger hiding in plain sight? Imagine the fabric of space itself as a bubbling, churning sea of invisible energy. Even in what we call a vacuum, particles flicker in and out of existence so fast they defy detection. This isn't science fiction, it's quantum vacuum fluctuations, where pairs of particles and antiparticles spontaneously emerge, collide, and vanish in fractions of a second. And here's the kicker, every time this happens, it releases tiny bursts of energy. Multiply this by the unimaginable vastness of space, and suddenly, you've got a potential explanation for dark energy's mysterious push on the cosmos. Now, how do we know this isn't just theoretical? The Casimir effect gives us a clue. Place two uncharged metal plates incredibly close together in a vacuum, and they'll mysteriously pull toward each other. Why? Because the space between them is too narrow for certain quantum fluctuations to occur. While outside the plates, those fluctuations keep happening, pushing the plates together with measurable force. It's proof that so-called empty space is anything but empty. But here's the problem. When physicists try to calculate how much energy these quantum fluctuations should contribute to the universe, the numbers explode into nonsense, predicting dark energy levels up to 10 to the power of 120 times stronger than what we actually observe. That's a 1 followed by 120 zeros. Even with our best theories, we're missing something fundamental. Are we misreading quantum mechanics? Is there a hidden cancelling effect we haven't discovered yet? Or could this bizarre discrepancy mean our entire understanding of space, energy, and reality is flawed at the deepest level? The quantum vacuum theory tantalizes with its elegance, an answer hidden in the fabric of reality itself. But until we crack the code on why the math refuses to add up, this cosmic energy crisis remains unsolved. What if the answer to dark energy was hiding in plain sight, written in the equations of history's most famous physicist, then tossed aside as a mistake? Enter Einstein's cosmological constant, a tiny number he scribbled into his theory of general relativity to keep the universe static. At the time, everyone believed the cosmos was unchanging and eternal. But when Edwin Hubble discovered the universe was expanding, Einstein called the constant his greatest blunder and crossed it out. The irony: decades later, astronomers found the expansion wasn't just happening, it was accelerating. Suddenly, that discarded idea became the leading explanation for dark energy. Think of the cosmological constant as an energy woven into space itself, a gentle but relentless push against gravity's pull. Unlike matter or radiation, which dilute as the universe grows, this energy stays constant. Every cubic meter of space, no matter how empty, contains the same tiny amount. That's why dark energy's influence was negligible in the early, dense universe, but now dominates as everything else thins out. It's like a hidden spring buried in the fabric of reality, slowly uncoiling to stretch space apart. Yet here's where physics hits a wall. When theorists calculate how strong this constant should be using quantum mechanics, the numbers spiral into madness, predicting an energy density 10 to the power of 120 times larger than what we observe. That's not just a rounding error, it's the worst mismatch in science. Some call it the vacuum catastrophe, a glaring sign that our theories are incomplete. Could there be an undiscovered symmetry cancelling out most of this energy? Or is the cosmological constant not truly constant at all, but a shadow of something deeper, like extra dimensions or a fluctuating quantum field? Einstein's abandoned idea now stands at the heart of cosmology's biggest mystery, a number so precise in its effects, yet so baffling in its origin. It fits the data beautifully, but until we understand why the math explodes into nonsense, the cosmological constant remains less an answer and more a cosmic placeholder, whispering that we're missing something fundamental about the universe. But what if dark energy isn't constant at all? What if it's something alive, shifting, evolving? A cosmic chameleon changing its strength over time. This is where quintessence slithers into the picture, a theory so provocative it could rewrite our understanding of the universe's fate. Unlike Einstein's static cosmological constant, quintessence is a dynamic scalar field, an invisible energy that ebbs and flows across space and time. Imagine it like an unseen ocean with waves that grow stronger or weaker, subtly altering how fast the universe expands. The name itself is a nod to ancient philosophy, Aristotle's fifth element, the mysterious substance filling the heavens beyond earth, air, fire, and water. And just like its namesake, modern quintessence is elusive, all-pervasive, and utterly unlike anything we've encountered. Here's why it's revolutionary. While the cosmological constant stays stubbornly uniform, quintessence interacts with itself, thinning out or concentrating in ways that could explain why dark energy seems stronger now than in the past. It's not just pushing space apart, it's dancing with it. Astrophysicists draw eerie parallels between quintessence and another phantom field, the inflaton. In the universe's first fractions of a second, this inflaton field drove exponential expansion during cosmic inflation, stretching space faster than light before vanishing without a trace. Could quintessence be its distant cousin, a late-blooming echo of that primordial frenzy? The similarities are uncanny. Both fields permeate all of space. Both exert repulsive gravity, and both could vanish or transform when their job is done. But here's the twist: unlike the inflaton, quintessence isn't just a relic of the past, it's actively shaping our future. Depending on how this field evolves, it might one day rip atoms apart in a Big Rip scenario or fade quietly into nothingness, leaving gravity to reclaim control. We don't know yet, and that's the thrill. Every measurement of distant supernova, every map of galaxy clustering, is a snapshot of this invisible tug of war. Yet quintessence isn't without its skeptics. Some argue it's too flexible, a theoretical bandage that can be stretched to fit any observation. Others point out we've never directly detected a scalar field like this. But if it's real, the implications are staggering. We wouldn't just be solving the dark energy puzzle, we'd be uncovering a new layer of reality, one where the universe breathes, pulses, and transforms in ways we're only beginning to glimpse. Now imagine a force so voracious it doesn't just push the universe apart, it devours it. This is phantom energy, dark energy's nightmare sibling, where the rules twist into something far more sinister. Unlike the steady push of the cosmological constant or the subtle dance of quintessence, phantom energy grows stronger as space expands. Its density isn't constant, it doesn't dilute, it multiplies. Picture pouring water into a cup, only to watch the water level rise faster the more you pour. Now scale that up to cosmic proportions, and you've got a recipe for the most violent in-game imaginable, the Big Rip. Here's how it unfolds. As phantom energy's grip tightens, gravity's glue fails first. Galaxy clusters, once bound by invisible threads of dark matter, are wrenched apart. Next, individual galaxies unravel, stars spiraling into the void like embers blown from a fire. Then solar systems, then planets. In the final moments, even atoms are torn asunder, nuclei stretched until protons and neutrons shatter. Space itself ruptures at every point, a fractal frenzy of disintegration. Time loses meaning, physics breaks, the universe doesn't just fade, it's shredded in a finite, fiery crescendo. But why would dark energy behave like this? The math allows it. Certain equations permit an energy field with a phantom equation of state, where pressure and density bend reality's rules. Some theorists tie it to exotic quantum fields or higher dimensional leaks. Others see it as a sign that our models of gravity need radical revision. Yet for all its dramatic allure, phantom energy faces fierce criticism. The biggest red flag: instability. Quantum fluctuations in such a field could spawn runaway particle pairs with infinite negative energy, birthing microscopic black holes or even tearing spacetime apart spontaneously. The universe in this scenario shouldn't have lasted past its first second. So is the Big Rip a prophecy or a mathematical mirage? Observations offer no clear verdict yet. The expansion rate, when measured with ultra-distant supernova and galaxy surveys, still fits multiple dark energy models, but phantom energy lingers as cosmology's ultimate cautionary tale, a reminder that the universe's fate might not just be strange but merciless. Whether it's real or not, the sheer possibility forces us to confront how little we truly understand about the fabric of reality. What if we've been staring at the missing energy puzzle backward? Instead of hunting for invisible forces, maybe our understanding of gravity itself is flawed. This is the radical premise of modified Newtonian dynamics, or a theory that dares to rewrite Einstein's rules where the cosmos gets weird. At the heart of MUND is a simple but audacious idea. Gravity doesn't weaken as sharply over vast distances as Newton or Einstein predicted. On the scale of galaxies, it clings tighter, pulling stars in their orbits without needing dark matter's phantom grip. The theory was born from an anomaly that's baffled astronomers for decades: galaxy rotation curves. According to Newton's laws, stars on the outskirts of a spiral galaxy should move slower than those near the center, like planets farther from the sun. But observations show something startling. Stars at the edge whip around just as fast. Dark matter was invented to explain this, an invisible halo propping up the speed. MUND offers a different fix. By tweaking gravity's math at ultra-low accelerations far weaker than what we feel on Earth, it makes galaxy rotations snap into place without invoking mysterious particles. And here's the kicker: MUND predicted these rotation curves before they were measured. It's not just retrofitting data, it's forecasting it. In some cases, it outperforms dark matter models, matching the elegant swirl of galaxies with eerie precision. Supporters argue this isn't coincidence. It's evidence we've been overcomplicating the cosmos with invisible stuff when the answer might be simpler. But scale up to galaxy clusters and MUND stumbles. These titanic gatherings of hundreds of galaxies move too fast for MUND-adjusted gravity to explain without ironically adding back some form of dark matter. Critics pounce on this as a fatal flaw. If your theory needs the very thing it seeks to replace, is it really a solution? Worse, man clashes with bulletproof evidence like the bullet cluster, where colliding galaxies visibly separate from their gravitational influence, proof of unseen mass. Then there's Einstein's shadow. General relativity has passed every test for over a century, from bending starlight to time dilation in GPS satellites. Man tweaks risk unraveling that tapestry without a clear replacement. Why would gravity follow Newton's laws here, Einstein's there, and some hybrid rule in deep space? Until man can smoothly bridge all scales without contradictions, it remains a tantalizing but incomplete rebellion against the dark energy paradigm. Yet its persistence is a testament to scientific dissent's value. Man forces us to question assumptions, to wonder if we've missed a subtle twist in gravity's plot. Even if it's wrong, wrestling with its challenges sharpens our search for truth. After all, the universe owes us nothing, not easy answers, not intuitive rules. Maybe the real mystery isn't just what's missing, but what we're still blind to in the laws we thought we knew. What if the missing energy isn't missing at all? It's just leaking into dimensions beyond our perception. This is the spine-tingling premise of brain cosmology, where the universe we know might be a mere slice of something far grander, floating in a higher dimensional space. Imagine an ant living on the surface of a pond. To that ant, the world is flat, two-dimensional. When a leaf falls into the water, the ant only sees the part touching its surface, completely unaware of the leaf's full three-dimensional shape. Now scale this up, our entire cosmos could be like that pond's surface, a brain drifting in a higher dimensional bulk, where gravity, unlike other forces, isn't confined to our brain. It seeps out, weakening its grip on us and creating the illusion of dark energy's repulsive push. String theory fuels this wild idea. In its framework, the universe has 10 or 11 dimensions, most curled up so tiny we'll never perceive them directly. But some could be vast, hidden realms just beyond our reach. Here's the twist: while particles like light and matter are pinned to our brain like ink on paper, gravity's carrier particles, gravitons, might slip between dimensions, diluting their strength. Picture a flashlight beam. On Earth, its light stays concentrated, but in fog it scatters, appearing dimmer. If gravity behaves similarly, leaking into extra dimensions, its apparent weakness in our universe could explain why galaxies fly apart faster than visible matter alone should allow. Evidence: the Large Hadron Collider once hunted for microscopic black holes, tiny gravity wells that would form if extra dimensions existed, sucking particles into the bulk. None appeared, but the search isn't over. Even stranger, if two brains collided in this higher dimensional space, the energy released could mirror the Big Bang. Our entire universe might be debris from a cosmic car crash in another dimension, yet skeptics pounce. If extra dimensions exist, why haven't we detected gravitational anomalies in lab experiments? Why does general relativity work flawlessly on solar system scales if gravity's strength is leaking? Brain cosmology dances on the edge of testability. Its math is elegant, its implications staggering, but until we catch gravity in the act of vanishing into the bulk, it remains a breathtaking what if in the dark energy saga. So is our universe a shadow cast by unseen dimensions, a cosmic spillover from realms we can't touch. Whether brain cosmology holds the answer or not, it forces us to reckon with a humbling truth: the missing energy might not be lost. We might just be looking in the wrong directions. Imagine the universe as a cosmic mirage, a shimmering illusion where every galaxy, every atom, is just a projection of information encoded on some distant, invisible boundary. This isn't the plot of a sci-fi movie. It's the holographic principle, a theory so mind-bending it suggests dark energy might be a glitch in the universe's underlying code. The idea sprouted from an unlikely place: black holes. When physicists calculated how much information a black hole could hold, They found it wasn't proportional to its volume, but to its surface area, like data etched onto a sphere instead of filling it. That revelation sparked a wild thought. What if reality itself works the same way? What if the three-dimensional cosmos we perceive is just a holographic projection from a two-dimensional surface at the edge of everything? Dive deeper and the math gets even stranger. The AD-S/CFT correspondence, a cornerstone of string theory, suggests a perfect duality between a gravity-filled universe and a quantum field theory living on its boundary. It's like realizing the movie you're watching isn't really happening on your screen. It's being streamed from a flat, pixelated code hidden behind the scenes. In this framework, dark energy could emerge from the way information on that boundary gets scrambled or stretched as the universe expands. Think of it like a cosmic zoom function. Enlarge a low-resolution image too much and it blurs, revealing gaps the original data didn't account for. Could dark energy be those gaps, the universe's way of coping with its own holographic limits? But how would this even work in practice? Picture the night sky as a colossal sphere surrounding us, its inner surface lined with microscopic pixels, storing all the information needed to construct reality. Every event, a supernova's flash, a planet's orbit, is just a translation of data from that outer shell. Dark energy, then, might be the energy cost of maintaining this illusion as space grows. The more the universe expands, the more strained the hologram becomes, requiring extra energy to keep the projection consistent. It's as if the universe is a computer struggling to render an ever larger simulation, consuming hidden resources to prevent crashes. Critics argue this is too abstract, a beautiful metaphor lacking smoking gun evidence. Yet tantalizing clues linger. Quantum entanglement, where particles instantly influence each other across vast distances, mirrors the holographic idea that separations in 3D space are illusions. Everything's connected on the 2D boundary. Even the universe's large-scale structure, with galaxies arranged in eerie, web-like patterns, aligns with holographic models of information networks. The holographic principle doesn't just offer a new angle on dark energy, it threatens to upend our very notion of reality. If true, we're not just missing energy, we're missing dimensions. The cosmos becomes a shadow play, its deepest secrets written in a language we're only beginning to decipher. Until we crack that code, the holographic universe remains a mesmerizing possibility. That the truth isn't out there among the stars, but etched on the edges of existence itself. What if dark matter and dark energy aren't separate mysteries at all, but two faces of the same cosmic enigma? Enter Chaplygin gas, an exotic fluid so bizarre it flips our expectations of physics on its head. Named after a Russian scientist who studied aerodynamics in the early 20th century, this theoretical substance behaves unlike anything in our everyday experience. Most materials push back when squeezed. Think of a balloon resisting as you press it. But Chaplygin gas does the opposite. When compressed, its pressure drops, creating a gravitational effect that can mimic both dark matter's grip and dark energy's push. It's as if the universe's missing energy isn't hiding in particles or fields, but swirling in an invisible, all-pervading fluid with split personalities. The math behind it is eerily elegant. In equations, Chaplygin gas is a perfect fluid with negative pressure, a property that lets it morph from behaving like cold dark matter in the early universe to acting like dark energy as space expands. Picture a cosmic chameleon. In dense regions, it clumps around galaxies, providing the gravitational scaffolding dark matter is famous for. But in the vast voids between galaxies, it thins out while maintaining enough negative pressure to accelerate expansion. One substance, two roles, unifying the universe's greatest puzzles with a single, sleek mechanism. Observations add tantalizing weight to the idea. When astronomers measure distant supernova to map the universe's expansion, Chaplygin gas models can fit the data nearly as well as standard dark energy theories. Even the cosmic microwave background, the afterglow of the Big Bang, shows patterns that align with certain Chaplygin gas scenarios, but there's a catch. For the theory to hold, this gas must avoid clumping too much in the early universe, or it would have distorted the delicate ripples we see in the CMB. Tweaking the equations to walk this tightrope between dark matter and dark energy behavior is a challenge that keeps physicists up at night. Yet the biggest hurdle might be the gas's sheer strangeness. Negative pressure isn't just rare, it defies intuition. In lab experiments, even the most exotic quantum fluids don't come close to mimicking Chaplygin gas's extreme properties. Some theorists argue it could emerge from higher dimensional physics or as a collective effect of undiscovered particles. Others speculate it's not a true gas at all, but a symptom of deeper gravitational laws waiting to be uncovered. Chaplygin gas remains a daring bet, a gamble that the universe's two darkest secrets might share a single, elegant solution. Whether it's a fleeting mathematical curiosity or the key to everything depends on one question: can something so counterintuitive really be out there, shaping the cosmos in plain sight? Until we detect its fingerprints directly, this ghostly fluid lingers at the edge of possibility, whispering that the answers we seek might be simpler and far stranger than we ever imagined. What if gravity isn't a fundamental force at all, but an illusion, a side effect of the universe's relentless slide into chaos? This is the startling premise of entropic gravity, a theory that reimagines gravity as an emergent phenomenon like temperature or pressure, born from the desperate scramble of particles trying to maximize disorder. At its core is entropy, the measure of a system's messiness, the reason coffee cools and eggs don't unscramble. But here's the twist: according to physicist Eric Verland, the same force driving your hot soup to room temperature might also be responsible for galaxies clinging together and space itself stretching apart. Verland's radical idea builds on a concept called the holographic principle, where the information describing a volume of space can be encoded on its boundary, like a cosmic DVD holding all the data needed to project a 3D universe. In this view, gravity arises when entropy gradients, differences in disorder, emerge near cosmic horizons, the edges beyond which information becomes inaccessible. Picture a black hole's event horizon. The entropy of the universe increases when matter falls in, and Verland argues similar entropy changes happen everywhere, even in empty space. When you hold an apple and feel its weight, what you're really sensing in this theory is the universe's way of rebalancing its disorder as the apple displaces space's microscopic degrees of freedom. Now apply this to dark energy. As the universe expands, new space forms, creating fresh cosmic horizons. Entropic gravity suggests that these horizons generate an outward force, entropic pressure, mimicking dark energy's repulsive push. It's as if the universe, in its quest for maximum entropy, is literally pushing itself apart to create more room for disorder. The math is tantalizing. Verland's equations reproduce the observed cosmic acceleration without invoking any mysterious dark energy. Instead, the acceleration becomes a natural consequence of information thermodynamics playing out on the largest scales, but critics aren't convinced. For one, entropic gravity struggles to explain the precise details of galaxy rotation curves without tweaking something dark matter handles effortlessly. Others point out that Verland's theory borrows heavily from established physics like Jacobson's 1995 work linking gravity to thermodynamics, but adds speculative leaps that haven't yet been tested. The biggest hurdle: entropic gravity predicts subtle deviations from Newton's laws in weak gravitational fields, deviations we haven't reliably detected. Until an experiment like LIGO or a space-based probe catches gravity misbehaving in a way only entropy can explain, the theory remains a beautiful but unproven sketch of an alternative reality. Yet the implications are profound. If gravity is emergent, then spacetime itself might be too, a kind of collective hallucination forged by countless microscopic interactions. Dark energy wouldn't be a missing ingredient, just a signature of how the universe organizes its chaos. It's a reminder that sometimes the most fundamental truths aren't forces or particles, but the invisible statistics of information whispering through the fabric of reality. What if the speed of light, the ultimate cosmic speed limit, wasn't always constant? Imagine rewinding the universe's clock to its earliest moments, when the laws of physics as we know them might have operated differently. This is the daring proposition behind time-varying speed of light theories, where light itself could have raced across the infant cosmos millions of times faster than today, dramatically reshaping how we calculate the universe's expansion and energy budget. The idea isn't as outlandish as it sounds. In the late 1990s, physicists Joe Megiddo and Andy Albrecht proposed that a faster speed of light in the early universe could solve some of cosmology's thorniest puzzles, like the horizon problem. Why does the cosmic microwave background look so uniform in all directions, as if distant regions had time to exchange heat, even though light shouldn't have had time to travel between them in the universe's infancy? If light moved faster back then, it could have bridged these gaps, eliminating the need for inflation's rapid expansion. But here's where it gets wilder. This tweak to light speed could also recalibrate our entire understanding of dark energy. One clue comes from the fine structure constant, denoted by alpha, a fundamental number governing how light and matter interact. Precise measurements of distant quasars suggest alpha might have been slightly different billions of years ago. If true, it implies other constants, like the speed of light or electron charge, could have varied too. Supporters argue this isn't just a minor adjustment, it's a revolution. A faster early light speed would change how we interpret redshift data, potentially explaining away dark energy as an illusion caused by misreading the universe's expansion history. But skepticism runs deep. Einstein's theory of relativity hinges on light's constancy. It's the backbone of modern physics. Altering it risks unraveling everything from GPS satellites to nuclear power. Critics also point out that quasar data on alpha is notoriously tricky to interpret, with some teams finding no variation at all. Even if alpha did fluctuate, linking it directly to light speed requires assumptions that leave many physicists uneasy. Yet the theory persists, fueled by its radical promise that the missing energy crisis might not stem from invisible forces, but from a fundamental misreading of light's ancient rhythm. Whether it's a brilliant insight or a beautiful dead end, one thing's certain: it forces us to question even the most sacred constants, reminding us that the universe's rules might be far more flexible than we ever dared to believe. Now picture a substance so alien it doesn't just lack mass, it possesses the opposite. Negative mass particles, a theoretical breed of exotic matter, defy every intuition about gravity we've ever had. While ordinary matter attracts, negative mass would repel, shooting away from apples, planets, and stars like magnets flipped to the wrong pole. The concept traces back to physicist Paul Dirac's groundbreaking work in the 1930s, where he theorized a vast, invisible ocean of particles filling the vacuum, the so-called Dirac Sea. Normally, these particles stay hidden, but if jostled, they could leave behind holes behaving like particles with negative energy, and by extension, negative mass. Here's where it gets wild. If such matter exists, it wouldn't just hover harmlessly, it could explain dark energy's repulsive force. Picture two negative masses interacting. Unlike positive masses that attract, they'd chase each other in a runaway acceleration, constantly pushing farther apart. Scale that up to cosmic proportions, and suddenly, the universe's accelerating expansion isn't driven by some mysterious field, but by a sea of these phantom particles invisibly shoving galaxies apart. Even more bizarrely, negative mass could warp spacetime in reverse, creating gravity-defying phenomena like wormholes or warp drives without needing infinite energy. Yet for all its tantalizing potential, negative mass remains squarely in the realm of what if. No experiment has ever detected it, and the math harbors nightmarish paradoxes. For instance, a single negative mass particle near Earth would theoretically fall upward, gaining speed indefinitely, violating conservation laws. Critics argue this makes the idea inherently unstable, a theoretical curiosity unlikely to reflect reality. Others counter that if negative mass is uniformly distributed, its effects might cancel out on small scales, only manifesting cosmically. The Dirac sea itself is contested. Modern quantum field theory replaced it with the sleeker, more flexible concept of quantum fluctuations. But the allure of negative mass persists, a ghost in the equations whispering that our understanding of matter and the universe's missing energy might be incomplete. Until we find a way to probe these shadows directly, negative mass remains one of physics' most electrifying dead ends, a solution that could explain everything if only it existed. What if dark energy isn't real, just a cosmic trick of the light? This is the provocative claim behind backreaction theory, where the universe's true expansion gets masked by its own lumpy, chaotic architecture. Picture pouring pancake batter onto a griddle. At first glance, it spreads smoothly, but zoom in, and you'll see bubbles, ridges, and thinning edges where the batter rises and falls unevenly. The cosmos behaves similarly. On massive scales, it's not a uniform sea of galaxies, but a frothy network of dense filaments and yawning voids stretching billions of light-years wide. And just like those pancake bubbles, these structures might distort how we perceive the universe's true expansion. Here's how the illusion works. When we measure cosmic acceleration, we're essentially tracking the average motion of galaxies over time. But averages can deceive. Voids, those vast, empty regions comprising most of the universe's volume, expand faster than the denser filaments and clusters around them. Gravity's grip is weaker there, so space stretches more easily. Meanwhile, crowded galactic superclusters resist expansion, slowing down nearby galaxies. When we mash these conflicting motions into a single number, we might misinterpret the result as uniform acceleration, when in reality, we're seeing a patchwork of local effects. Proponents like physicist Thomas Buchert argue this backreaction could mimic dark energy's signature without invoking any exotic physics. Their models suggest inhomogeneities, the universe's lumpiness, create a kind of fake acceleration that builds over time. It's as if you tried to measure the speed of cars on a highway by averaging sports cars and trucks stuck in traffic. You'd get a misleading picture of how fast things are really moving. But critics strike back with a simple rebuttal: scale. Even the largest voids and filaments only tweak the global expansion rate by a fraction of a percent, nowhere near the 7% needed to explain dark energy's observed effect. Simulations show backreaction alone can't replicate the precise redshift patterns seen in supernova data, and cosmic microwave background measurements, which capture the universe's baby photos, align too perfectly with standard dark energy models to ignore. Yet the debate refuses to die. Newer research hints that backreaction might grow more significant over billions of years, like compound interest on a cosmic loan. Some even propose that our entire observable universe sits inside a particularly massive void, a Hubble bubble, where local expansion differs radically from the broader cosmos. If true, we could be cosmic parochials, mistaking our neighborhood's quirks for universal laws. The stakes couldn't be higher. If backreaction is real, it wouldn't just erase dark energy. It would force us to rewrite how we model the universe's structure, abandoning the smooth approximations that underpin modern cosmology. But until someone proves these inhomogeneities pack enough punch to hijack the expansion rate, dark energy retains its crown. The truth might lie somewhere in between, not a flawless illusion, but a reminder that the universe's grandest narratives are always filtered through the messy reality of its architecture. What if space and time aren't fundamental but stitched together by something far stranger? Enter emergent spacetime, a theory where the very fabric of reality is woven not from invisible threads, but from the ghostly connections of quantum entanglement. Picture the universe as a cosmic quilt, where each stitch is a bond between particles, instantly linking them no matter how far apart they drift. Now imagine that these stitches don't just connect things, they create the canvas itself. Spacetime, in this view, isn't the stage for physics, it's the performance emerging from a deeper dance of quantum information. At the heart of this idea is a radical reshuffling of cause and effect. Instead of entanglement happening within spacetime arises from entanglement. Think of it like a bustling city. From a distance, you see streets, traffic, and life unfolding in orderly patterns. But zoom in, and you realize the city only exists because of countless individual choices, people moving, interacting, building connections. Similarly, spacetime's smooth geometry could be the large-scale illusion of countless quantum entanglements humming beneath the surface. The math behind this is as elegant as it is mind-bending. Physicists like Mark van Romsdonk have shown that if you take a quantum system and entangle its particles in just the right way, the equations naturally generate something that looks like curved spacetime, reproducing Einstein's general relativity as an emergent effect. It's like discovering that the rules of chess aren't arbitrary but naturally spring from how the board itself is constructed. And here's where dark energy sneaks in. If spacetime's structure depends on entanglement, then as the universe expands and these quantum links stretch thin, the energy needed to maintain the cosmic quilt could manifest as dark energy's repulsive push. Visualizing this isn't easy, but qubits, the basic units of quantum information, offer a clue. Imagine each qubit as a node in a vast cosmic web, entangled with others in a shimmering network. The more entangled they are, the tighter the fabric of spacetime. But as expansion pulls these nodes apart, the web strains, requiring extra energy to keep the connections intact. Dark energy, then, might be the cost of preserving reality's coherence in an ever-growing universe. Critics argue this is still speculative, a beautiful framework lacking experimental proof. Yet tantalizing hints abound. The AD/CFT correspondence, a cornerstone of string theory, already suggests a deep link between entanglement and geometry. Even black holes, those gravity-heavy monsters, obey laws eerily similar to thermodynamics, as if their immense curves in spacetime are just the surface ripples of deeper quantum ties. Emergent spacetime doesn't just offer a new angle on dark energy, it threatens to redefine reality itself. If true, we're not merely missing energy, we're missing dimensions. The cosmos becomes a hologram, its true workings hidden in quantum threads we're only beginning to trace. Until we learn to read that code, emergent spacetime stands as a profound reminder. Sometimes the deepest truths aren't written in the stars, but in the invisible bonds stitching them together. What if dark matter and dark energy aren't just neighbors in the cosmic mystery? What if they're the same thing wearing different masks? Enter dark fluid, a theory so audacious it dares to merge the universe's two greatest enigmas into a single, shape-shifting substance. Unlike ordinary matter or energy, dark fluid doesn't play by fixed rules. Its behavior flips depending on where it is, clumping like cold, dark matter in the crowded streets of galaxies, then stretching like phantom energy in the desolate voids between them. Imagine a cosmic chameleon that's solid when you grab it but turns to mist when you try to hold on tight. The math behind this is as elegant as it is strange. Dark fluid is modeled as a perfect fluid, with negative pressure a property that lets it defy intuition. In dense regions like galaxy clusters, gravity squeezes the fluid, increasing its pressure until it acts like an invisible glue, holding stars in orbit just as dark matter does. But in the empty expanses between galaxies where gravity's grip weakens, the fluid's negative pressure takes over. It repels rather than attracts, driving space apart like dark energy. One substance, two faces unifying the cosmos's biggest puzzles with a single, flexible equation. Astronomers first glimpsed hints of this duality in the motions of galaxy clusters. When they mapped the distribution of mass in the universe, they noticed something odd. The pull needed to keep galaxies clustered matched dark matter's predictions, but the push driving expansion aligned with dark energy's effects. Dark fluid offers a slick solution, no need for two separate mysteries when one adaptable material can do both jobs. Even the cosmic microwave background, that fossilized glow from the Big Bang, shows patterns that dark fluid models can replicate without introducing new particles or fields. But there's a catch. For dark fluid to work, it must walk a razor-thin line between clumping too much or too little. If it's too sticky, it would distort the early universe's delicate density fluctuations. If it's too slippery, galaxies would never have formed. Tweaking the equations to balance these extremes is like tuning a piano where every note must resonate across 14 billion years of cosmic history. Critics argue that dark fluid is a band-aid, a clever math trick that glosses over deeper questions. Why would a single substance have such schizophrenic behavior? What physical mechanism could flip its properties so perfectly? And why haven't we detected any trace of it in labs or particle colliders? Supporters counter that dark fluid isn't just convenient, it's economical. Nature favors simplicity, and a universe where one dark entity wears two hats is arguably cleaner than inventing two unrelated phantoms. The boldest implication. Dark fluid suggests we've been misled by our own measurements. What if the universe's expansion isn't accelerating because of some repulsive force, but because we're misreading how gravity behaves in extreme environments? It's a humbling thought that the cosmos's greatest secret might not be missing energy, but a fundamental misunderstanding of how the pieces we've already found fit together. Until we can pin down this elusive fluid's true nature, it remains a tantalizing what-if at the frontier of cosmology, a reminder that sometimes the most elegant solutions are also the strangest. Hidden beneath the equations of particle physics lies a breathtaking symmetry, one so powerful it could rewrite the rules of reality itself. Supersymmetry, or SUSY, isn't just another theory. It's a mathematical siren song, whispering that every particle we've ever discovered has a secret twin. Electrons, quarks, photons, they'd all be paired with heavier, unseen sparticles lurking just beyond our detection. And here's the kicker. These shadowy siblings might hold the key to the universe's missing energy. The beauty of SUSY lies in its elegance. It smooths out the jagged edges of the standard model, solving problems physicists have wrestled with for decades. Take the Higgs boson's mass. Quantum calculations suggest it should be catastrophically heavy, yet somehow it's feather-light. SUSY fixes this by introducing superpartners that cancel out these quantum corrections like cosmic counterweights. But the real magic, dark matter, the lightest particle, often called the neutralino, could be stable, electrically neutral and invisible, matching dark matter's profile perfectly. Yet for all its promise, SUSY has a credibility crisis. The Large Hadron Collider, designed partly to hunt these superpartners, has come up empty after years of smashing protons at record energies. Critics pounce, if particles exist, why haven't we seen even a flicker? Supporters counter with cosmic patience. SUSY particles might simply be heavier than current colliders can reach, or they could decay so fast they leave no trace. Some theories even suggest particles could be hiding in extra dimensions, only detectable through their gravitational whispers. The stakes couldn't be higher. If SUSY is real, it wouldn't just explain dark matter. It could unify nature's forces into a single framework, revealing a universe more symmetrical than we ever dreamed. But with every passing year of null results, the theory's once gilded edges tarnish slightly. the universe, it seems, enjoys teasing us with possibilities just out of reach. Whether Sussy survives or fades, its legacy is secure, a daring reminder that sometimes the most beautiful equations are the ones that force us to confront how much we still don't know. Picture a particle so feather-light it could dance on a sunbeam, yet it might hold the answer to dark energy's deepest secrets. Meet the axion, a hypothetical wisp of matter so light it makes electrons look like boulders. Born from a puzzle in quantum physics called the strong CP problem, axions were originally dreamed up to explain why the universe doesn't tear itself apart at the atomic level. But here's the twist: these ghostly particles might also be the architects of cosmic acceleration, their subtle oscillations nudging space itself apart over billions of years. The strong CP problem is one of physics' quiet embarrassments. Quantum theory predicts that the strong nuclear force, the glue holding protons and neutrons together, should distort particles in ways we've never observed. It's like designing a car that should veer violently left every time you start it, yet mysteriously drive straight. Axions solve this by introducing a new field that fine-tunes nature's equations, cancelling out these distortions with the precision of a cosmic thermostat. But the real magic happens when you scale this idea up. If axions exist, they wouldn't just lurk inside atoms, they'd flood the universe, forming an invisible sea so vast that even their minuscule mass could add up to something staggering. What makes them perfect dark energy candidates is their bizarre behavior. Unlike ordinary particles, axions would oscillate not just in space, but through extra dimensions predicted by string theory. These oscillations could create a pressure that counteracts gravity on cosmic scales, like a trillion tiny springs embedded in the fabric of reality. Even stranger, axions might interact with light in ways that turn entire galaxies into cosmic searchlights. When photons pass through magnetic fields like those around black holes or neutron stars, they could momentarily morph into axions, creating faint energy signatures we're only now learning to detect. The hunt is already underway. Experiments like ADMS use supercooled cavities to listen for axions converting into microwave photons, tuning their detectors like radios scanning for a whisper in a hurricane. Others scour the heavens for anomalous starlight polarization or unexpected gamma-ray bursts that might betray axions' presence. Even the cosmic microwave background could hide clues, subtle temperature fluctuations that match axion-driven models of the early universe. Yet skepticism lingers. Axions are notoriously slippery. Their predicted mass spans a range so wide it's like searching for a needle in a billion haystacks. Some theorists argue they're too light to account for dark energy's observed effects, while others propose modified versions, axion-like particles that could fit the bill. The truth might lie somewhere in between, not pure axions, but a family of related particles weaving a tapestry we've only begun to unravel. Whether axions solve one mystery or a dozen, their story embodies the boldness of modern physics, a discipline that can conjure particles from equations and chase them across galaxies. If they're out there, they're not just hiding in the darkness. They might be the darkness itself, whispering secrets at the edge of detection. Think of the universe's vacuum not as empty nothingness, but as a chameleon capable of sudden, dramatic transformation, like water flash freezing into ice or steam condensing into droplets. This is the spine-tingling premise of vacuum metamorphosis, where dark energy might not be a steady force, but the aftershock of reality itself undergoing a cosmic phase shift. The math behind this is as elegant as it is unsettling. Just as water molecules rearrange when temperatures drop, the quantum fields permeating all of space could have abruptly reconfigured at some critical point in cosmic history, flipping the universe's expansion into overdrive. The smoking gun, evidence from the Planck telescope. When scientists mapped the cosmic microwave background, the afterglow of the Big Bang, they noticed subtle anomalies in how matter clumped across the universe. These patterns align eerily with predictions made by vacuum metamorphosis models. suggesting a pivotal moment around 9 billion years ago when the vacuum's energy density suddenly dropped like a cosmic pressure valve releasing. The result, an accelerated expansion that looks like dark energy but is really the universe settling into a new, lower energy state. Think of it as cosmic downsizing on a galactic scale. What makes this theory so compelling is its parallel to everyday physics. We're used to phase transitions, liquid to gas, magnetized to non-magnetized. But applying this to the vacuum itself is revolutionary. In the early universe, a similar transition, electroweak symmetry breaking, gave particles their mass. Vacuum metamorphosis proposes that history repeated, not with particles this time, but with spacetime's underlying fabric. The trigger could have been as simple as the universe cooling past a critical threshold as it expanded, or as exotic as a hidden quantum field finally decaying after eons of instability. Yet mysteries linger. Why did this phase change happen so late in cosmic history? Most transitions occur in the universe's fiery infancy, not its middle age. And if the vacuum really shifted, why hasn't it left more dramatic imprints, like bubbles of new physics expanding at light speed? Some theorists argue we're seeing only the first tremors of a slower, grander transition, still unfolding, one that could eventually rewrite the laws of physics in ways we can't yet fathom. Vacuum metamorphosis doesn't just tweak our dark energy models, it turns them inside out. Instead of hunting for some elusive substance, we might be witnessing the universe itself evolve in real time, its very foundations quietly rewriting the rules. Whether this theory holds or not, it forces us to confront a breathtaking possibility that the cosmos isn't just expanding, it's growing up. Imagine a form of matter that doesn't just defy gravity, it defies the very rules of reality as we know them. This is the bizarre realm of unparticles, a hypothetical substance so strange it doesn't even act like matter in the traditional sense. Unlike protons, electrons, or any familiar particles, unparticles don't have a fixed mass or size. They're scale invariant, meaning they look the same whether you zoom in or out, a fractal enigma haunting the edges of particle physics. And here's the wild twist. This ghostly stuff might be secretly puppeteering the universe's expansion, its subtle gravitational antics perfectly mimicking dark energy's repulsive push. The concept of unparticles sprang from a collision of particle physics and abstract mathematics. In 2007, physicist Howard Georgi proposed that hidden sectors of reality, dimensions or forces beyond the standard model, could contain fields that don't break down into tidy particles. Instead, they'd manifest as a smeared-out, ethereal presence, more like a cosmic fog than discrete objects. Picture trying to grab smoke with your hands. The harder you squeeze, the more it slips through your fingers. Unparticles behave similarly, resisting any attempt to pin them down to a specific energy or location. What makes them a contender for dark energy's crown is how they interact, or rather, barely interact, with everything else. Unparticles couple to ordinary matter through impossibly weak forces, so feeble that they'd fly through planets like ghosts through walls. But on cosmic scales, their collective influence could be profound. Because they're scale invariant, unparticles don't dilute as the universe expands. Their energy density stays constant, just like dark energies, creating a steady outward pressure that stretches spacetime itself. It's as if the cosmos is filled with an invisible, intangible fluid that never thins out, no matter how vast space becomes. To grasp how this might work, think of the universe as a rubber sheet stretched taut. Ordinary matter creates dents in that sheet. Gravity wells where planets and stars sit. Unparticles, though, don't make dents. Instead, they tweak the sheet's elasticity, subtly loosening its fabric so it naturally wants to expand. Over billions of years, that slight softening could accelerate the universe's growth without any need for a cosmological constant or quintessence field. Yet proving unparticles exist is a nightmare. Their weak interactions make them nearly undetectable, like trying to spot a single whisper in a hurricane. Some theorists suggest hunting for them through precision measurements of neutron stars, where their presence might subtly alter gravitational waves. Others propose that high-energy particle collisions could, for a split second, leak energy into the unparticle sector, leaving telltale gaps in momentum conservation. So far, no luck, but if unparticles are real, they'd rewrite more than just cosmology. They'd force us to rethink what matter even means, blurring the line between particles and pure, unfiltered energy. The irony is delicious. After centuries of cataloging atoms, quarks, and leptons, we might be on the verge of discovering that the universe's dominant ingredient isn't made of particles at all. Unparticles challenge the very language we use to describe reality, offering a haunting reminder. Sometimes the most profound truths aren't just hidden in the shadows, they're the shadows themselves. Black holes aren't just cosmic vacuum cleaners, they might be the universe's most unexpected power sources, leaking energy so exotic it could fuel the cosmos's accelerating expansion. This is the startling intersection of two colossal mysteries, the black hole information paradox and dark energy. At the heart of it all is Hawking radiation, the faint glow of particles theorized to escape black holes' gravitational clutches over unimaginable eons. But what if this radiation isn't just a slow leak? What if it's a transformative force woven into the fabric of spacetime itself? Let's rewind to the universe's infancy. In the chaotic aftermath of the Big Bang, countless primordial black holes, some as small as asteroids, may have formed from pockets of ultra-dense matter. Unlike the stellar mass black holes we know today, these ancient relics would have been evaporating since the beginning, their Hawking radiation subtly infusing the cosmos with energy. Here's the twist: as these black holes shrink, their radiation doesn't just vanish. According to recent work by physicists like Eric Verland and others, the quantum information they release could manifest as a repulsive force, counteracting gravity on cosmic scales. It's as if every evaporating black hole is exhaling dark energy into the universe. But how does this connect to the information paradox? Imagine a black hole as a locked library. Every book tossed inside, every particle swallowed, seems lost forever, violating quantum mechanics' rule that information can't be destroyed. Hawking radiation initially appeared to confirm this nightmare, suggesting information truly vanishes when black holes evaporate. But breakthroughs in string theory and holography hint that the information isn't gone, it's encoded in the radiation itself, scrambled like a cosmic cryptogram. This resolution implies that Hawking radiation isn't random noise. It's a structured outpouring of energy that could carry subtle gravitational effects. Over billions of years, the cumulative push from countless evaporating black holes might stretch spacetime like an invisible tide. The cosmic microwave background offers eerie clues. Tiny temperature fluctuations in this afterglow map the early universe's density variations, regions where primordial black holes could have clustered. Some theorists argue these anomalies align too neatly with models where black hole evaporation fuels cosmic acceleration. Even stranger, the timing fits. As the universe expanded and cooled, the evaporation rate of primordial black holes would have hit a critical threshold around the same epoch dark energy's influence became dominant. Coincidence or cosmic causation, yet skeptics pounce on the gaps. If primordial black holes are leaking so much energy, why haven't we detected their final explosive bursts? And why does the math suggest their collective output falls short of the dark energy we observe? Supporters counter that we might be missing the forest for the trees. The true effect could emerge from how evaporating black holes alter the vacuum's quantum structure, a process we're only beginning to model. Whether this theory holds or not, the implications are staggering. Black holes, long cast as the universe's ultimate endpoints, might secretly be its engines, driving expansion through their slow-motion unraveling. The information paradox, once a philosophical headache, could unlock dark energy's origins. It's a reminder that in cosmology, the solutions to our greatest puzzles often lurk in the last places we'd think to look. What if the universe has a hidden twin, a mirror world where every particle, every force is just slightly out of sync with ours? This isn't just sci-fi speculation. It's the spine-tingling premise of mirror universe theory, where dark energy might not be missing at all, it could be leaking in from a parallel reality. Picture two soap bubbles pressed together, their surfaces nearly touching but never quite merging. Now imagine one bubble's gravity subtly warping the other, creating strange bulges and repulsions. That's the essence of this idea, a shadow cosmos tugging on ours from an unseen dimension. Its gravity flipping to anti-gravity as it crosses the boundary, pushing our universe apart. The math behind this is as elegant as it is mind-bending. In certain string theory models, mirror universes aren't just possible, they're inevitable. Every particle in our world could have a doppelganger in the mirror realm, identical in mass but opposite in charge and other quantum properties. Normally, these twins would never interact, locked in separate dimensions. But if the barrier between worlds has even microscopic flaws, tiny rips or wrinkles in space-time, their gravitational influence could bleed through. And here's the twist: while normal matter attracts, mirror matter might repel. It's inverted physics manifesting as the cosmic push we call dark energy. Visualizing this is easier than you'd think. Take the way magnets behave. Opposite poles attract, but matching poles push apart. If our universe and its mirror counterpart share a similar symmetry, their gravitational poles could repel, creating an anti-gravity effect that scales with the universe's expansion. The more space grows, the more mirror matter's influence seeps in, like water soaking through cracks in a dam. Yet proving this isn't just poetic speculation is a nightmare. Mirror matter, by definition, would be nearly invisible. It doesn't emit or absorb light in our universe. The only way to detect its gravitational echo would be through precision measurements of cosmic expansion or anomalies in galaxy rotations. Some experiments are already hunting for these fingerprints. When the LIGO gravitational wave detector picks up ripples in spacetime, theorists comb the data for unnatural patterns, repeats, or delays that might signal waves bouncing off a hidden mirror dimension. Even the cosmic microwave background could hold clues. If mirror photons occasionally stray into our universe, they'd leave faint temperature asymmetries in the sky's oldest light. The biggest hurdle, testability. Mirror universes are crafted to be just beyond our reach. By design, they don't interact strongly with our world. Critics argue this makes the theory unfalsifiable, a cosmic, just-so story. But supporters counter with a daring thought experiment. If mirror matter exists, it could explain more than dark energy. The infamous missing baryon problem, where half the universe's predicted normal matter can't be found, might simply be matter hiding in plain sight, flipped into the mirror realm during the Big Bang's fury. Whether mirror universes are real or not, the theory forces us to confront a humbling possibility. That dark energy isn't a flaw in our equations, but a message from a world we can't see. It's gravity whispering through the walls of reality. Until we find a way to peer beyond those walls, the mirror remains cosmology's most tantalizing riddle, a reflection of everything we still don't know. Neutrinos are the universe's most elusive particles, nearly massless phantoms that stream through planets and stars like they aren't even there. Billions pass through your body every second, leaving no trace. But what if these cosmic ghosts, in the right conditions, could clump together on scales so vast they rewrite the rules of gravity itself? This is the startling promise of neutrino condensates, where these ethereal particles might form a shadowy quantum sea stretching across the cosmos, their collective behavior bending spacetime in ways we never imagined. At the heart of this theory is a quantum quirk. When particles are cooled to ultra-low energies, they lose their individual identities and merge into a single, coherent state, a condensate. We've seen this in labs with Bose-Einstein condensates, where atoms chilled to near absolute zero behave as one giant quantum wave, Now stretch that idea to cosmic proportions. If neutrinos, with their tiny but non-zero masses, were somehow chilled and concentrated in the early universe, they could have formed a galaxy-spanning condensate, an invisible quantum fluid woven through the fabric of space. And here's where it gets wild. Under certain conditions, this neutrino sea could exert negative pressure, acting like a repulsive gravitational force that drives cosmic acceleration. The neutrino mass hierarchy adds another layer of mystery. We know neutrinos come in three flavors: electron, muon, and tau, each with slightly different masses. But the exact ordering of these masses, known as the hierarchy problem, remains one of particle physics' great unsolved puzzles. If the lightest neutrino is far lighter than the others, it could be the perfect candidate to form a low-energy condensate, its quantum waves overlapping across billions of light-years. The heavier neutrinos, meanwhile, might behave more like traditional dark matter, clumping around galaxies. Together, they could form a two-tiered dark sector, one part glue holding galaxies together, the other part fuel pushing them apart. Evidence for this idea is thin but tantalizing. The cosmic neutrino background, a relic sea of low-energy neutrinos left over from the Big Bang, hints at the raw material for such a condensate. If even a fraction of these neutrinos interacted in just the right way, perhaps through some undiscovered force or symmetry-breaking event, they could have coalesced into this exotic state. Cosmological simulations show that neutrino condensates could reproduce dark energy's observed effects without fine-tuning, their repulsive gravity naturally scaling with the universe's expansion. Yet skeptics raise tough questions. How could neutrinos, which barely interact with anything, form a condensate in the first place? Wouldn't their weak interactions prevent the necessary cooling and coherence? Some theorists propose that unknown physics in the early universe, extra dimensions, hidden fields, or phase transitions, might have provided the perfect cradle for this quantum phenomenon. Others argue that if neutrino condensates exist, they should leave subtle fingerprints in the cosmic microwave background's polarization patterns, a signature upcoming telescopes like the Simons Observatory could hunt for. The boldest implication: neutrino condensates could unite two of physics' biggest mysteries, dark energy and neutrino mass, into a single elegant framework. Instead of inventing new particles or fields, we'd be repurposing the universe's most abundant yet elusive inhabitants, giving them a starring role in the cosmic drama. Whether this theory holds or not, it's a reminder that sometimes the answers we seek aren't hidden in the shadows, they're streaming through us at the speed of light, waiting for the right conditions to reveal their secrets. What if gravity isn't just a tug between nearby objects? What if every star, every galaxy, every speck of dust in the cosmos somehow reaches across the void to shape how matter moves right here, right now? This radical idea, known as non-local gravity, tears up the rulebook Einstein gave us and replaces it with something far stranger: a universe where the past, present, and future are entangled in a gravitational web stretching across space and time. Imagine throwing a rock into a pond and watching the ripples spread outward, except in this case, the pond is all of existence, and every ripple that's ever existed still lingers, subtly tugging on every new splash. This isn't just wild speculation. The seeds were planted centuries ago by philosopher Ernst Mach, who argued that inertia, the resistance of objects to changes in motion, isn't an intrinsic property but a cosmic conversation. When you push a coffee cup across a table, the reason it resists isn't just because of its mass. It's because every atom in the universe is somehow whispering to it, shaping its behavior. Einstein called this Mach's principle, and though he never fully embraced it, hints of it linger in general relativity's equations. Non-local gravity takes this further, suggesting that gravity itself is a collective memory of the universe's entire history, not just a snapshot of masses nearby. Quantum mechanics adds fuel to the fire. We already know particles can be spookily linked through entanglement. instantly influencing each other across vast distances. If quantum non-locality, this defiance of local cause and effect, can shape the behavior of tiny particles, why couldn't it scale up to gravity itself? Some theories propose that gravitational fields aren't generated by masses in isolation, but emerge from the universe's total energy distribution, past and present. It's as if every galaxy that ever existed leaves a fingerprint on space-time, and those fingerprints never fade. The implications for dark energy are staggering. If gravity's strength depends on the universe's global structure rather than local matter, the accelerating expansion might not need dark energy at all. Instead, as the cosmos grows and its history stretches, the gravitational memory of earlier, denser epochs could fade, creating the illusion of a repulsive force. Picture an elastic band losing its snap over time. What looks like something pushing could just be the grip of the past slowly letting go. Some models even suggest this could explain why dark energy seems to kick in late in cosmic history, as the universe's expansion dilutes the gravitational influence of its denser youth. Yet challenges loom. Non-local gravity theories often rely on complex, untested math, stitching together general relativity and quantum mechanics in ways that make physicists uneasy. Without experimental proof, they risk becoming elegant but unfalsifiable stories. Supporters argue that subtle anomalies in galaxy rotations or gravitational lensing could betray non-local effects, hints that gravity isn't playing by local rules. Others hunt for clues in the cosmic microwave background, where the universe's infant murmurs might encode traces of this grand gravitational entanglement. Whether non-local gravity holds the key or not, it forces us to confront a profound shift in perspective. The universe might not be a collection of isolated events, but a single, interconnected tapestry, where every gravitational nudge carries echoes of everything that came before. If true, dark energy isn't a mysterious substance, it's the cosmos remembering itself, its history written not in stars or dust, but in the invisible threads stitching reality together. Picture the universe in its first trillionth of a second, a seething cauldron of energy so intense it twisted the very fabric of reality like taffy pulled too fast. In that unimaginable chaos, space-time itself might have formed microscopic cracks, cosmic strings, defects so dense a single inch could outweigh Mount Everest. These aren't strings in the familiar sense, but ultra-thin filaments of pure space-time curvature, leftover scars from when the cosmos underwent its very first phase transitions. Like cracks forming in ice as water freezes, these relics could still be lurking undetected across the universe today, vibrating at nearly the speed of light and radiating faint gravitational shudders with every oscillation. What makes cosmic strings tantalizing dark energy candidates is their bizarre relationship with vacuum energy. Unlike ordinary matter, strings wouldn't dilute as the universe expands. Their energy stays locked in their one-dimensional structure, creating a network of persistent gravitational lenses and time warps. Some theories suggest these strings could be superconducting, channeling currents of primordial charge that interact with magnetic fields on galactic scales. Others propose they're knotted into intricate loops, each knot acting as a microscopic battery storing vacuum energy from the Big Bang. Over billions of years, as these loops slowly decay, they might release that pent-up energy into the cosmos, fueling the acceleration we attribute to dark energy. But here's where observations throw cold water on the most dramatic possibilities. If vast networks of cosmic strings crisscross the universe, their gravity would distort the cosmic microwave background in telltale ways, sharp, linear anomalies that our telescopes like Planck have failed to detect. The absence of these fingerprints has largely ruled out string networks dense enough to fully explain dark energy. Yet all hope isn't lost. While kilometer-scale strings are unlikely, ultra-thin strings, thinner than a proton and stretched across billions of light years, could still evade detection while collectively contributing to the vacuum's energy budget. The hunt for these ghostly filaments continues in unexpected places. When black holes merge, the gravitational waves they emit could carry subtle echoes if a cosmic string happened to vibrate nearby. Pulsar timing arrays networks of ultra-precise cosmic clocks are scanning for nanosecond glitches that might betray a string's passage through our galaxy. Even the strange, filamentary structures of the cosmic web, where galaxies cling to invisible threads, could hint at ancient string influences woven into the universe's large-scale architecture. Cosmic strings dance on the edge of fantasy and physics, a reminder that the answers to our greatest mysteries might be hiding in the scars of spacetime itself. Whether they're the key to dark energy or just another dead end, their legacy endures, a testament to the universe's ability to encode its secrets in the most unexpected places. What if dark energy isn't a steady force at all, but a cosmic pendulum swinging between strength and weakness in an eternal rhythm? The standard lambda model treats dark energy as a constant, Einstein's cosmological constant, lambda, a fixed energy density woven into space itself. But what if that's the universe's greatest oversimplification? Enter variable dark energy, a radical reimagining where the very fabric of reality breathes, its energy rising and falling in cycles that could rewrite the fate of everything. At the heart of this idea are scalar fields, invisible, all-pervasive entities that fill space like an ethereal mist. Unlike constants, these fields can evolve, their energy densities shifting as the universe ages. Picture a ball rolling down a hill. If the hill's slope changes, the ball's speed does too. Scalar fields work similarly, their energy density determined by the shape of their potential, a mathematical landscape defining how they interact with spacetime. In thawing models, the field starts frozen, trapped in a high-energy state like a marble stuck in syrup. As the universe expands, the syrup thins, and the marble begins to roll, slowly releasing energy that mimics dark energy's repulsive push. But flip the script and you get freezing models. Here, the field starts rolling fast, its energy dominating early on, but as expansion stretches spacetime, the field slows, like a skater gliding to a halt on frictionless ice. The energy density plateaus, freezing into a near-constant state that resembles the cosmological constant. The difference? These models predict subtle fluctuations in dark energy's strength over cosmic time, leaving fingerprints in the way galaxies cluster or supernova brightness varies with distance. Evidence for this variability is thin but tantalizing. Some analyses of supernova data suggest dark energy might have been slightly weaker in the universe's youth, while others find hints of oscillation in the cosmic microwave background's large-scale patterns. The trouble is, these signals are buried in noise, like trying to hear a whisper in a hurricane. Future telescopes like ESA's Euclid or the Vera-Rubin Observatory could change that, mapping billions of galaxies to trace dark energy's influence across billions of years with unprecedented precision. Critics argue these models introduce unnecessary complexity. Why fix what isn't broken? Lambdactum works shockingly well for most observations, but supporters counter that nature rarely favors simplicity for its own sake. After all, we once thought the Sun revolved around a static Earth until wobbles in planetary motion forced a rethink. Could dark energy's apparent constancy be another cosmic illusion, a temporary plateau in a grander cycle? The stakes couldn't be higher. If dark energy varies, the universe's fate might not be a slow fade or a dramatic rip, but a series of crescendos and silences, expansion accelerating, then decelerating in a dance without end. It's a reminder that the cosmos rarely bows to our neat categories. What we call a constant might just be a snapshot of something far more dynamic, a universe that's not just expanding but breathing. Gravity is the universe's great sculptor, the force that shapes galaxies, bends light, and pins planets to their orbits. But what if its fundamental particles, the hypothetical gravitons, are doing something far stranger than just transmitting this pull? Picture a state of matter so bizarre it defies classical physics. A Bose-Einstein condensate where countless particles merge into a single quantum wave, losing their individual identities and behaving as one. Now imagine this happening not in a lab with chilled rubidium atoms, but on a cosmic scale, with gravitons condensing into a ghostly superfluid stretching across the cosmos. This isn't science fiction, it's a daring theory suggesting that dark energy's push might be the gravitational force itself, transformed into something unrecognizable by the universe's expansion. The math behind this is as tantalizing as it is complex. In particle physics, Boson's particles like photons or gravitons that can occupy the same quantum state are prime candidates for condensation. When cooled to near absolute zero, they collapse into the lowest energy state, forming a coherent quantum entity. But here's the twist. The universe's expansion might naturally create the perfect conditions for gravitons to condense without needing extreme cold. As space stretches, gravitons could redshift, their wavelengths diluting until they overlap, merging into a vast, low-energy condensate permeating the vacuum. Unlike any condensate, this graviton sea would exhibit collective behavior. In this case, a negative pressure eerily similar to dark energy's repulsive effect. Quantum gravity experiments offer faint whispers of support. Though gravitons remain undetected, theories like loop quantum gravity and string theory predict their existence as carriers of gravitational force, much like photons mediate electromagnetism. Some models suggest that in the extreme curvature near black holes or during the universe's infancy, gravitons could have interacted strongly enough to form transient condensates. Even today, their residual effects might linger, subtly tweaking how gravity operates on cosmological scales. For instance, if gravitons condense unevenly, clumping more in cosmic voids than near galaxies, their collective push could explain why empty regions of space seem to repel matter rather than attract it. Critics, however, raise glaring questions. Gravitons, if they exist, are expected to couple so weakly with matter that detecting them is nearly impossible, let alone proving they've condensed. And without a full theory of quantum gravity, the mechanics of graviton condensation remain speculative at best. Yet supporters argue that absence of evidence isn't evidence of absence. The Higgs boson was once deemed untestable too, until the Large Hadron Collider smashed protons with enough energy to reveal it. Similarly, next-generation gravitational wave detectors or precision measurements of the cosmic microwave background might uncover anomalies pointing to graviton behavior beyond Einstein's framework. The most mind-bending implication: if graviton condensation is real, it blurs the line between force and substance. Gravity wouldn't just shape the universe, it would literally become part of its fabric, a dynamic medium evolving with expansion. Dark energy wouldn't be an external field or a cosmological constant, but gravity's own shadow cast by its quantum nature at the largest scales. It's a poetic twist. The force that pulls us down might also be the hidden hand pushing the cosmos apart. Until experiments catch up with theory, graviton condensation remains a beautiful enigma, a reminder that the universe's deepest secrets often lurk in the spaces between what we can measure and what we can only dream. What if the key to dark energy isn't hidden in equations or undiscovered particles, but written on the very edges of reality itself? The holographic dark energy theory takes the mind-bending idea that our universe might be a projection and pushes it further, suggesting dark energy's strength is directly tied to the cosmic event horizon, the maximum distance light could ever travel before space's expansion outruns it. Picture the universe as a sealed sphere, its surface area encoding all the information needed to construct the 3D world we perceive. Now imagine the energy density of that universe isn't determined by what's inside the sphere, but by the size of the sphere itself. That's the core of holographic dark energy. the universe's accelerating expansion isn't driven by some mysterious substance, but by the growing information deficit as the cosmic horizon stretches. The math behind this is startlingly elegant. In standard physics, vacuum energy density should be constant, a fixed value per cubic meter of space, but holographic models argue it's actually inversely proportional to the square of the horizon's radius. As the universe expands and its horizon grows, the energy density inside gradually decreases, creating an effective repulsive force that matches dark energy's observed effects. It's as if reality is a stretched rubber sheet. The more you pull, the thinner and more energetic it becomes at its edges, pushing everything outward from the boundary. But this leads to the infamous coincidence problem. Why now? The universe is nearly 14 billion years old, yet dark energy's dominance began only around 5 billion years ago, a cosmic blink of an eye in the grand timeline. If dark energy's strength is tied to the horizon, why did it wait so long to take over? Some theorists argue this isn't a flaw but a clue. The holographic principle might require a phase transition, a moment when the universe's information storage hit a critical threshold, flipping dark energy from background noise to the dominant force. Others propose a feedback loop. As the horizon expands, it alters the quantum entanglement network encoding reality, which in turn tweaks the horizon's growth rate. It's a cosmic chicken and egg scenario where cause and effect blur. Critics aren't convinced. If holographic dark energy is real, why does its predicted energy density still rely on arbitrary constants? And how does it square with quantum field theory's vacuum energy calculations, which famously overshoot dark energy's observed value by 120 orders of magnitude? Supporters counter that the holographic framework naturally suppresses these runaway values by tethering energy to spacetime's informational limits, a built-in regulator missing from conventional theories. The most profound implication isn't just about dark energy, it's about reality's very nature. If holographic dark energy is correct, the universe isn't just expanding, it's recalculating itself at the edges, its fundamental energy reset by the cosmic horizon's relentless growth. We might not be living in a universe filled with dark energy, but on a hologram that's running out of pixels. The deeper we probe, the clearer it becomes. The answers we seek might not lie in the stars, but in the invisible boundaries stitching them together. Deep in the equations of the early universe lies one of physics' most stubborn mysteries. Why is there anything at all? After the Big Bang, matter and antimatter should have annihilated each other perfectly, leaving only light in a featureless void. But here we are, in a cosmos teeming with galaxies, stars, and planets, proof that somehow matter won. This tiny imbalance, known as Baryon asymmetry, might hold the key to another cosmic riddle: dark energy. Picture a cosmic seesaw. For every billion particles of antimatter in the infant universe, there were 1,000,001 particles of matter. That 1 in a billion surplus is all that survived annihilation, the raw material of everything we see today. But what if that same asymmetry didn't just leave behind matter? It left behind something else, a shadow of unpaired energy, simmering in the vacuum, slowly stretching spacetime apart. This is the daring idea linking baryon asymmetry to dark energy, where the universe's very existence might be fueling its own expansion. The foundation traces back to physicist Andrei Sakharov's 3 conditions for matter's survival: a universe out of thermal equilibrium, processes violating matter-antimatter symmetry (CP violation), and interactions that don't conserve baryon number. Experiments like those at CERN LHCb detector have found hints of CP violation, tiny deviations where particles and antiparticles decay at slightly different rates. But here's the twist: these same asymmetries could have seeded dark energy. If CP violation left behind not just matter but imbalanced quantum fields, their residual energy might permeate space as a repulsive force. Imagine a cosmic bank heist. Matter and antimatter were supposed to cancel out like perfectly matched withdrawals and deposits. But if the ledger was subtly rigged, if antimatter withdrew slightly faster, the bank would be left with an unexplained surplus. Dark energy, in this analogy, might be the interest accumulating on that unbalanced account, a latent energy from the universe's original asymmetry. Critics argue the math doesn't quite add up. The energy scales of baryogenesis and dark energy differ by orders of magnitude. But proponents counter with a stunning possibility. The same exotic particles that triggered matter's dominance, like hypothetical leptoquarks or sterile neutrinos, might have decayed into long-lived fields that only recently began dominating the cosmos. It's as if the universe planted time-release capsules of energy at its birth, set to activate billions of years later. The implications are staggering. If baryon asymmetry and dark energy share a cosmic blueprint, we might be staring at a unified answer to two of physics' greatest why questions: why we exist and why the universe is tearing itself apart. The answers could be written in the same faint cracks in reality's symmetry, waiting to be decoded in particle colliders or the swirling patterns of the cosmic microwave background. Until then, the link remains a tantalizing thread pulling us deeper into the labyrinth of the cosmos's hidden logic. Imagine tapping into the infinite energy bubbling beneath the fabric of space itself, a limitless power source hiding in the so-called empty vacuum. This is the tantalizing promise of zero-point energy, a concept that's fueled countless sci-fi fantasies but sits squarely on the razor's edge between groundbreaking physics and wishful thinking. At its core, zero-point energy is the leftover jitter of quantum fields. Even at absolute zero, when all classical motion stops, particles continue to flicker in and out of existence like cosmic static. The math suggests the vacuum is seething with energy, and if we could somehow mine it, the rewards would be incomprehensible. A single cubic centimeter of empty space is estimated to contain more energy than all the matter in the visible universe. So why aren't physicists scrambling to bottle this cosmic free lunch? The devil's in the details, specifically renormalization. When you calculate the total zero-point energy by summing up all possible quantum fluctuations, the result isn't just large, it's infinite. That's obviously nonsense, so theorists use a mathematical trick called renormalization to sweep these infinities under the rug, subtracting them away like cosmic accounting errors. The process works beautifully for predicting particle interactions, but it leaves the vacuum energy's absolute value undefined. What's left after renormalization is either zero or a tiny residual that might align with dark energy, but we have no principled way to derive that number from first principles. Casimir's famous experiment offers a glimpse of zero-point energy's reality. Place two metal plates nanometers apart in a vacuum, and they're pushed together by the sheer pressure of quantum fluctuations excluded from the gap between them. It's a measurable effect, but extracting usable energy from this is like trying to power a city by harvesting the whispers between two panes of glass. The forces involved are microscopic, and scaling them up would require engineering feats bordering on magic, like building a machine that could somehow push against the vacuum itself. Theories abound for how zero-point energy might connect to dark energy. Some speculate that dark energy is the renormalized remnant of these quantum fluctuations, a tiny fraction that leaked into gravity's equations. Others propose that our universe's vacuum energy is locked in a metastable state, like a glass supercooled below its freezing point, waiting to decay into a lower energy configuration. If that happened, the release could rewrite the laws of physics overnight, but mainstream cosmology remains skeptical. The gap between zero-point energy's theoretical infinity and dark energy's observed value is the worst mismatch in science, a discrepancy of 120 orders of magnitude. That's not just wrong, it's screamingly, catastrophically wrong. Either we're missing something fundamental about quantum fields, or vacuum energy simply isn't the answer to dark energy. Yet the allure persists. From warp drives to perpetual motion machines, zero-point energy captures imaginations because it hints at a universe richer than our equations can describe. Maybe one day we'll crack the code, turning quantum whispers into cosmic revelations. Until then, it remains the ultimate what if, a reminder that sometimes the most promising solutions are the ones just out of reach. Picture our entire universe not as everything that exists, but as a single soap bubble adrift in an endless cosmic froth. One accidental pocket of stability in a seething, infinite ocean of inflating space. This is the mind-bending premise of eternal inflation, where the Big Bang wasn't a unique event but a routine hiccup in a multiverse that's been expanding exponentially forever. According to this theory, what we call our universe is just one region where inflation, that violent hypergrowth of space-time, happened to slow down, allowing matter, stars, and us to form. Beyond our bubble's edges, the frenzy continues unchecked, spawning new universes with every passing instant, each with its own random cocktail of physical laws. Visualizing this isn't easy, but imagine a pot of water boiling violently. Most bubbles pop instantly, but a few stabilize, growing large enough to float to the surface. In eternal inflation, space itself is that boiling pot, and universes like ours are the rare, lucky bubbles that didn't burst. The scary part, we might not be alone in this foam. Neighboring bubble universes could be drifting perilously close, their edges pressing against ours like balloons squeezed together in a box. If two bubbles collide, the aftermath wouldn't be subtle. It would send shockwaves rippling through space-time, potentially leaving scars in the cosmic microwave background or distorting the large-scale structure of galaxies. The hunt for these collision scars is already underway. Astronomers scour the CMB for bizarre circular anomalies, temperature fluctuations that resemble bruises from a cosmic fender bender. One controversial claim pointed to a cold spot in the southern sky, a region chillingly devoid of galaxies that some theorists argue could be the imprint of a long-ago bubble collision. Skeptics counter that statistical flukes can't be ruled out, but the tantalizing possibility lingers. We might one day find hard evidence that we're not just in a universe but adrift in a multiverse. Yet eternal inflation isn't without its paradoxes. If new universes are constantly budding off an eternally inflating background, the multiverse becomes infinite in both space and time. An infinity breaks probability. Every conceivable event, no matter how unlikely, must happen somewhere. There'd be universes where you're reading this script backward, or where gravity repels instead of attracts. Critics argue this makes the theory untestable by definition, dissolving into a fuzzy, anything-goes metaphysics. Supporters fire back that we're simply grappling with the consequences of a reality too vast for human intuition. The most unsettling implication: if eternal inflation is real, our bubble might not be permanent. Just as regions of false vacuum decayed to spawn our universe, our pocket of stability could one day rupture, consumed by a new wave of runaway inflation. One moment, galaxies; the next, an unfathomable void rewriting the laws of physics. It's a reminder that the cosmos owes us no guarantees. Our existence might be as fleeting as a soap bubble's shimmer, a temporary configuration in an endless cycle of creation and destruction. Until we find those telltale bruises on the sky, eternal inflation remains a breathtaking gamble that the greatest mysteries of our universe might be answered by looking beyond its edges. What if the missing energy isn't lost, it's just an oversight in the code running our reality? The simulation hypothesis takes the cosmic mystery of dark energy and flips it into something straight out of a sci-fi thriller. We might be living in an artificial universe, and the gaps in our physics are nothing more than rounding errors in some unfathomable computer. Philosopher Nick Bostrom's famous trilemma lays out the chilling logic. Either civilizations never reach technological maturity, they choose not to run ancestor simulations, or we're almost certainly living in one. Given the mind-boggling number of simulated realities a post-human society could create, the odds tilt unnervingly toward option 3. Think of dark energy as a cosmic buffer overflow. In a simulated universe, every particle, every force interaction requires processing power. To save resources, the simulation might approximate physics at extreme scales, just as video games render distant landscapes in low detail. Quantum indeterminacy, where particles exist in fuzzy superpositions until observed, could be another optimization trick. Why calculate the exact position of every electron in a galaxy no one's looking at? These shortcuts would leave artifacts tiny discrepancies between the simulation's rules and its output. Dark energy's unexplained push might be the universe's version of a floating point error, a glitch where energy conservation isn't perfectly enforced. Even the holographic principle fits this eerie narrative. If our three-dimensional world is a projection from a two-dimensional boundary, like a cosmic GPU rendering a VR headset, dark energy could be the computational cost of maintaining that illusion as the simulation's memory expands. The more space grows, the more processing strain, manifesting as an apparent energy deficit. It's like a video game lagging when too many objects spawn at once, except here, the lag is accelerating galaxies apart. Critics dismiss this as metaphysics masquerading as physics. After all, if the universe is a simulation, its creators could have hidden the glitches perfectly. But supporters counter with a provocative thought experiment. The very fact we've hit a wall with dark energy suggests the simulation's limits. Maybe some truths are deliberately obfuscated, or perhaps we're meant to notice. Either way, the simulation hypothesis doesn't just reframe the missing energy, it reframes reality itself, turning cosmology into the ultimate detective story. Are we chasing shadows, or is the universe quietly confessing it's not what it seems? From ghostly unparticles to colliding bubble universes, we've journeyed through 30 mind-bending explanations for the cosmos's missing energy, each one more audacious than the last. Some theories tweak gravity's rules, others summon hidden dimensions, and a few dare to suggest we're living in a glitching simulation. Yet after centuries of searching, the universe guards its secret fiercely. Dark energy remains the ultimate cosmic sleight of hand, a puzzle that transforms every time we think we've grasped it. What's startling isn't just the diversity of ideas, it's how many fit the data, at least partially. Modified gravity aligns with galaxy rotations but stumbles on clusters. Quantum vacuum energy explains repulsion but drowns in infinities. Even the wildest contenders, like neutrino condensates or holographic horizons, dangle just enough predictive power to keep us hooked. This isn't a sign of failure, it's a testament to human ingenuity. When nature throws a paradox this profound, we don't retreat, we imagine harder. So where does that leave us? Suspended between certainty and wonder, armed with equations that both illuminate and obscure. Perhaps the answer lies in a theory not yet scribbled on a chalkboard, or in some cosmic truth so counterintuitive we've yet to even frame the right question. That's the thrill of cosmology. Every dead end is a detour, every contradiction a clue. As we zoom out past superclusters, past the cosmic microwave background, past the edge of the observable universe, the question lingers like starlight in an expanding void. What's pushing everything apart? Maybe it's all of these theories, maybe it's none. For now, the mystery belongs to you. Which explanation sends your mind spinning? A shadowy fluid, a crack in space-time, or something stranger still? Drop your favorite theory in the comments, hit subscribe, and let's keep unraveling the universe's greatest tricks, one wild idea at a time. The cosmos isn't done surprising us yet.